Hello, my name is Noah Siegel, and today my group and I are going to try and make it easier for you all to understand the topic of rotational motion in physics. An important part of rotational motion in physics is this thing called torque. If you're unfamiliar with the word torque, I want you to think of something more simple like force, for example, because technically torque is the force on a rotational scale. So for example, if I had a string attached to my finger with a tennis ball that went around it in a perfect circle, the force that keeps the tennis ball going around in the circle is called torque. To make a topic like this more understandable, my friend Cameron is going to introduce an easy to understand example involving a figure skater turning in a circle and something called angular momentum, which you'll speak more about now.
Hi everyone, my name is Cameron Hubert. I'm a member of Group 7. We chose to focus our video explanation on Module 8, which is rotational motion and torque or force, which Noah previously talked about. Our explanation of the concept is going to be an example of a figure skater. You guys are probably familiar with it, in which we're asked to calculate the angular momentum and torque required to stop the skater from spinning. I'm going to introduce part A of the example, and I'm going to give it over to our next group mate. Her name is Marina. She's going to go through and do the calculations. So just to start, we're asked to solve for angular momentum, which is the product of the momentum of inertia and the angular velocity. So the momentum of inertia being the body's resistance to an acceleration on an axis, and the axis being the person's body, skater's body, and angular velocity, which is the amount of revolutions completed per second by the skater. So I'm going to go ahead and write down the example and just go through a few things. Okay, so part A reads, what is the angular momentum of a figure skater spinning at 3.5 revolutions per second with arms in close to her body, assuming her to be a uniform cylinder with a height of 1.6 meters, a radius of 13 centimeters, and a mass of 60 kilograms. So to go over what we're given the angular velocity, which I explained as being the revolutions, so 3.5 revolutions per second. We are given the height of the skater in meters, which is 1.6 meters. We are given the radius of the skater, which is 13 centimeters, which as we know is not in SI units, so we do the simple calculation and turn it to meters, which is 0.13 meters. We are given the mass of the skater in kilograms, which was explained as being 60. So, to calculate the angular momentum of a skater, we're going to use the equation L, being the angular momentum, equals the uppercase I, that one's the moment of inertia, times, it's a Greek omega sign, it's a lowercase w. I'm guessing you guys have seen it in the homework. So, that one represents angular velocity. So I'm going to send you over to my classmate. Her name's Marina. She's also going to be setting up this in terms of this equation and solving for the angular momentum. Thanks a lot.
Hi, my name is Marina Taitano, and I'll be showing you how to solve part A of our figure skater example that Cameron introduced, which is solving for angular momentum. Since the problem is assuming she is a uniform cylinder, I went ahead and sketched a rough diagram on how that would kind of look with the givens. Since we're using the equation of angular momentum, we first need the moment of inertia. So we'll use the equation 1/2 times mass times radius squared, and plugging in our givens, that would be 60 kilograms times 1/2 times 0.13 meters squared, and that will come out to 0.507 kilograms times meters squared. The angular velocity is already given by 3.5 revolutions per second, but since it's a cylinder, we need this in radians. So we need to multiply 3.5 by 2 pi radians per revolution, which will give us 7 pi. That's also 21.99, but I'm just going to keep it simple for now and keep it at 7 pi and multiply it later. So since we have these, we're going to plug them into the angular momentum equation. So that will be 0.507 kilograms times meters squared times 7 pi, and that will come out to 11.15 kilograms times meters squared over seconds. And that is the angular momentum. Next, Samuel will be presenting how to solve part B of the problem, which is the torque required to slow her to a stop.
Hey everybody, my name's Sam. I'm going to be helping you guys with part B of this problem, figuring out how much torque is required to slow down the figure skater when she's not moving her arms. How much torque is required to slow her to a stop in 5.8 seconds, assuming she doesn't move her arms? The formula for torque is torque equals angular momentum divided by time. The angular momentum was found in part A, 11.149, and the time is given in the problem, 5.8 seconds. So the torque necessary to slow her to a stop is 1.922 Newton meters. Hopefully you guys all have a little bit of a better understanding of rotational motion in physics, and more specifically angular momentum and torque. Thanks for watching. Bye.